Hi, I'm Mike Stanzik and this is Digital Electronics Classroom. In this video we're going to take a look at Kirchhoff's voltage law. And this law says essentially that the voltage changes around a loop, the total voltage change, has to be equal to zero. And we're going to look at some diagrams to show us how that works and then do an example problem. So let's get to it. Kirchhoff's voltage law, or KVL. So it says the total voltage change around a loop equals zero. So let's draw a little picture here of a circuit. It has 3 resistors and a battery. Then I like to box some nodes so we can see all the voltage nodes in this circuit. Right, perfect. And we can label these nodes A, B, C, and D. And so what this means is that if we start here at D, and then we go around this circuit, we know that at D there's a certain voltage, which we call the node voltage. And so if I go across the battery into A, that'll be a change in voltage. If I go across to B, that's another change in voltage. And if I go across to C, that's another change. And then to D, a final change. But we end up at D again, and that's where we started. So the voltage at D is the same as it was. And so we have to get back to exactly where we started with these 4 changes. And so if we have changes that bring the voltage up, we have to have changes that bring the voltage back down so that we end up at the same spot. Or if they initially bring the voltage down, then we have to have changes that bring the voltage back up so that we end again at that same spot. And this is the idea of Kirchhoff's voltage law, because at a node the voltage is the same. And so that's what we're seeing here. Now, another way we can state this is that, well, when we go around here, like I said, we either have a rise in voltage or we have a drop in voltage. And so another way to state this law is that the rises around a loop equal the drops. And so I've shortened it a little bit here, but we're saying that the total sum of the voltage rises around the loop are equal to the total sum of the voltage drops around the loop. All right, so how do we know if it's a rise or a drop? Well, we need to do 2 things. First off, we need to make a direction in which we are evaluating our loop. And so in this case, I'm going to go around clockwise. And the second thing we have to do is we have to make polarity markers on each of our elements. And so perhaps the polarity markers look like this. So now as I go around the loop, what I notice is, I'm going to start again at D. When I go through the battery, I go from a minus to a plus. And so a minus to a plus would signify a rise in the voltage. Now this might not be a rise in actuality, but because we are labeling it this way in our equation, we're going to write it on the rise side. And if we got it wrong, all that's going to happen is in our answer, the answer is going to be negative. And so we'll have to look out for that. So we want to write this as a rise. And then we have this second one here, it goes from plus to minus, so that's a drop. And then I go from minus to plus as I go around, that's a rise. And then plus to minus, that's a drop. So we have 2 rises and 2 drops when we go around this circuit. Okay. So I'm going to redraw this just a little bit. and so it's a little bit easier to see, and we'll get those nodes out of the way, and we'll just take a look at the elements here. So we'll call this V0. We said it was plus minus like that. We'll call this R1. We said that was plus minus like that. This is R2, and that was minus plus like that. And then this one is R3, and it was plus and minus like that. And we're evaluating the loop in this direction. So when I evaluate this loop, I want to start out with saying that the rises are equal to the drops. And I'll go ahead and write the voltages that are rises as I go around the loop. And we said that V0, the battery, was a rise, and also R2, which we'll write as V2, its voltage. And then the drops are then R1 and R3, so that would be V1 plus V3. So that would be the equation that we would have. Now, we might know some information already about this circuit, and we indeed have to know something if we want to solve for an unknown. So for instance, let's say that we know that right here, this V1 is equal to 5 volts. Let's say that this V2 here is equal to negative 3 volts. And let's say that this V3 here is equal to 7 volts. Now, why would this be negative 3? What do we mean that it's a negative voltage? Well, the way we wrote this is that we said that the bottom node here is higher voltage than the top node because we gave that a plus and this is a minus. But if the top node was actually higher volts than the bottom node, higher voltage, then it would be a negative value for the voltage, and that's what it's saying. It's saying that the top node here is 3 volts higher than the bottom node. But just because we labeled it differently, we get a negative answer there, and that's totally fine. And so we can leave it like that. Okay. So let's go ahead and plug this into our expression then. V0 is what we're looking for. V2 we said was negative 3. V1 is a 5, and V2 is V3 is a 7. And so I have 12 on the right, and then a minus 3 that comes over is 3 more. So solving that, we get V0 is 15 volts. And so that's positive 15 volts. And so that's how we can use Kirchhoff's loop law to figure out what a value is inside a loop using the voltage drops around the loop must equal 0. Thanks for watching. I hope you found this valuable, and until next time, have a wonderful day.